Captions in English, please. So this is the sixth video on chapter 2, and it's about significant figures. So in math, we don't worry about significant figures, but in chemistry, it involves a lot of measurements that have uncertainty. And so before we do calculations with units, dimensional analysis type of calculations, we need to learn which digits in a measurement are considered significant. So there are rules that you will need to learn by heart. So all non-zero integers always count as significant figures. For example, in the measurement 546 grams, there is 3 significant figures, the 5, the 4, and the 6. In the measurement 7.815 centimeters, there is 4 significant figures. So every digit here is non-zero and counting as significant. So what about zeros? That's the one that are more troublesome. And so there are rules for them. The leading zeros are those zeros we call placeholders. It's the zeros that precede all non-zero digits. And so these do not count as significant figures because they're really there to show you where is the decimal point. For example, in 0.000247 miles, there is only 3 significant figures, the 2, the 4, and the 7. All those zeros are not significant. In 0.075 inches, there is 2 significant figures, the 7 and the 5. The zeros are not significant. They're only here to show you where is the decimal point. Trailing zeros, also placeholders, are zeros at the right end of the number. They are significant only if the number contains a decimal point. So you need to be very, careful about, watching for, do we have a decimal point in that number or not? Because that will determine if the zeros are significant or not when they are trailing zeros. For example, in 9.300 liters, there is 4 significant figures because we see the decimal point, and so the zeros will be significant, the zeros that come after the 3. In 150 kilograms, there is only 2 significant figures because the 0 here is not significant. To make it 3 significant figures, you would have to change that and make it 150 with a dot kilograms. And then there is 3 significant figures in that number because the decimal point is shown, and so it makes a point in saying that the 0 here is significant. So be very careful and not put your dots, as a habit. You have to be conscious about the fact that it means that the 0 is significant. In the example 435,000 meters, there is only 3 significant figures, the 4, the 3, and the 5. The zeros that come after that are not significant because there is no decimal point shown. And again, if you wanted to make those zeros significant, then you would put the decimal point to the right of the last 0. And with the decimal point shown like that, it would make it 6 significant figures. All zeros would count and the non-zero digits. Sandwich zeros are zeros between non-zero digits. These always count as significant figures. So it's those zeros between, in this example, between the 2 and the 3. So in 20,345 seconds, there is 5 significant figures. In 1.009 centimeter, there is 4 significant figures. All digits count here. And when you have numbers written in scientific notations, all the digits in the coefficient, remember the coefficient is the decimal part of the scientific notation. So all digits in the coefficient are significant. For example, in 2.07 times 10 to the 8 meters, there is 3 significant figures, the 2, the 0, and the 7. Of course, the exponential part is not taken into account when you are deciding when you are deciding about significant figures. In this example, 2.05460000 times 10 to the negative 6 liters, there is 8 significant figures. All of the digits here are significant. The sandwich zero and the trailing zeros. Because we see the decimal point, you can also think about it like this. Exact numbers have an infinite number of significant figures. So they have an unlimited number of significant figures. And what are exact numbers? It's those in a definition or those that have been counted instead of measured. So when you're counting objects like pencils here, there are 7 pencils. The 7 here is what we call an exact number. You cannot have 7.5 pencils, right? It's always 1 pencil or 0 pencils. 12 donuts here equals a dozen. That's all exact numbers. 12 are exact. The 1 dozen is also an exact number. And that's also a definition, right? We know that 1 dozen is always 12 things. Examples of definitions are the equalities that relate a unit to another. And 1 inch is equal to 2.54 centimeters exactly. Or for example, 1 meter is 1,000 millimeters. Or 1 kilogram is 1,000 grams. These are examples of definitions, and all the metric prefixes all the metric prefixes unit lead to exact definitions. And also within the English system, it's also exact definitions. This example here of 1 inch equals 2.54 centimeters is between the English and the metric system, but it's considered to be exact. So let's go through a concept check. Please think about this on your own before you watch the answer. It is important that you practice before you watch the answer. So how many significant figures are contained in the following measurement? Number A, so 0.00310 inches. How many significant figures? So the zeros to the left are called leading zeros. These are not significant. And then you start counting from the 3, the 1, and then the 0 as well, the 0 after the 1. So here there would be 3 significant figures. The 3, the 1, and the 0 to the right. Another way to see it is that we see the decimal point. So the 0 to the right, which is a trailing 0, is significant then. Example B, 1.0825 liters. So here there is mostly non-zero digits and then a sandwich 0, and these always count. So there is 5 significant figures in that number or measurement. 2,000 kilometers. How many significant figures? Only 1. Because there is no decimal point shown. So that tells you the zeros are not significant here. 10.3872 meters. Again, that's a sandwich 0 here, and it's all significant. So that's 6 significant figures. 2.3030 times 10 to the 4th miles. This is a number in scientific notation, and we've said that the coefficient of the number in scientific notation contains all significant digits. So the 2, the 3, 0, 3, 0 are all significant figures. So that's 5 significant figures in that measurement. 5,000 gallons with the decimal point shown. So that makes the 0 significant. So then there is 3 significant figures. 1 liter equal 1,000 milliliter. That's by definition, it's been established to be exactly true. So these are considered exact numbers. So they have an unlimited number of significant figures. You cannot give a number there. It's unlimited and it will not limit the number of significant figures. So when performing calculations, you will need to round your answers to indicate the correct number of significant figures. And there are two rules. If the number after the digit to be rounded, so you look only at the digit that is after the one to be rounded. If it is less than 5, then the digit remains the same. And if the number after the digit to be rounded is greater than or equal to 5, then the digit will have to be rounded up. And it is important that you understand, you only look at the one digit after. That's it, you don't look further. So let's go through some examples here and round the following to the number of significant figures specified. So 3.210, let's round it to 3 significant figures. So you start counting from the left. So you start with the 3, 2 and 1, that's 3 significant figures. So we need to stop at the 1. What comes after the 1 is a 0, so you round down and you keep the 1 as it is. And the rounding will be then 3.21. 29.9887. Let's round this to 2 significant figures. So you start counting from the left. The 2, the 9, and that's already 2 sig figs. What comes after the 9 is another 9. That's above 5, so you need to round up. So the 29 will have to be rounded up to 30. But to make it 2 significant figures, you need to show the decimal point, otherwise the 0 would not be significant. So this would be rounded as 30 with the decimal point shown. 36.7, rounded to 2 significant figures. So you count from the left, the 3, the 7. That's it, 2 sig figs. You need to look at what comes after. It's a 7. You need then to round up. It's above 5, so you round up. The 6 needs to be rounded up to a 7, so that's going to be 37. 350 rounded to 1 sig fig. So that means we need to keep the 3. What comes after the 5 is a 5. What comes after the 3 is a 5. And that means you need to round up. So the 3 needs to become a 4. And then what is important here is to not forget to keep the 3 or the 4 here in the hundreds place, right? The 4 is in the hundreds place, so you need to show the zeros to show that it's in the hundreds place. And you don't show the decimal point because you want only 1 sig fig. Here, the zeros are not significant, so it's one significant figure. One last example, at 1000, let's round this to 2 significant figures. So that means you keep the 1 and then the 0 after that. What comes after the 0 is another 0, so you round down. And so it would be 1, 0. But you cannot show that in the regular way of writing numbers. You will need to use the scientific notation here to show that it's 2 significant figures. And so you will change it to 1.0. This way you show that it's 2 significant figures, and times 10 to the third to show that it's 1000. So when you're doing calculations, typically you may have several calculations to do before the final answer. And it is very important that you do not round until the end of the problem. This is important because it may change the final answer. In a series of calculations, carry the extra digit through the final result and then round off at the final result only. This means that you should carry all the digits and show that are shown on your calculator until you arrive at the final number, the answer. And then you round off using the procedures in rule 1 and 2 that we just saw in the previous slide. So how to deal with significant figures when you are doing multiplication and division or division. So for multiplication or division, the number of significant figures in the result is the same as that in the measurement with the smallest number of significant figures. So that's the rule that you need to learn by heart. When you're multiplying or dividing or doing both, you need to keep the smallest number of significant figures at the end. So you will need to look at all measurements involved in the calculation and find the one with the smallest number of significant figures. Example 1.342 times 5.5. In 1.342 there is 4 significant figures. In 5.5 there is 2. You do this on your calculator and you obtain 7.381. That's the calculator answer. The calculators don't know about significant figures. You have to do the work. And here, the smallest number of significant figures was 2 sig figs. So that's why we show here that we will need to keep the 7 and the 3. That's 2 sig figs. What comes after the 3 is an 8. So you will need to round up. And so the final answer will be 7.4 with 2 significant figures. Another example, 56.55 times 0.920 divided by 0.00430. Let's determine the number of significant figures in each of the numbers. So 4 sig figs for the first one. The second number has 3 sig figs, and the 0 that is significant is not the leading one, the first 0, it's the trailing one, the one to the right, right? So 9, 2, and the last 0 to the right are significant. In the third measurement here, there is again leading zeros that are not significant, and you start counting from the 4, 3, and the last 0 are significant. So that's 3 significant figures in that measurement. So the least number of significant figures is 3. The calculator answer is that. And so we need to keep 3 significant figures. So let's count. We keep the 1, the 2, and then the 0 is the third sig fig. What comes after the 0 is a 9, so you need to round up. So we will keep the 1, the 2, and then it's going to be a 1. And this one is in the hundreds place, so we need 2 zeros after that to show that it's 12,100. And here we see that there is 3 significant figures, the 1, the 2, and the 1. You do not show the decimal point because otherwise that would make it 5 significant figures. Let's do a concept check to verify that you know how to use those rules. And so write the answer of the calculations below using the correct number of significant figures. So practice this on your own before you watch the answer. This is important to practice. So 2.1 times 2.010 times 10 to the third. Here, what's in the parentheses is simply a number in scientific notation. So we have 2 numbers. Let's determine the number of significant figures in each. First one has 3 significant figures. The second one has 4, right? All zeros are significant in this case because it's the coefficient of a scientific notation. And you can also tell that the first 0 is a sandwich 0, the last 0 is a trailing 0. So the least number of sig figs is 3. The calculator answer is that 4,643.1. So we need to keep 3 sig figs. So we keep the 4, the 6, and the 4. What comes after the 4 is a 3, so we need to run down. And so the 4 stays a 4, and the final answer will be 4,640. That gives us 3 sig figs, and we do not show the decimal point. Otherwise, it would make 4 sig figs. Next example, 100.0 divided by 200 times 1.0 times 10 to the third. Again, we have some number in scientific notation here. We have three numbers here. So let's find out the number of sig figs for each. 100.0 has 4 sig figs. All zeros are significant because you see the decimal point. 200 has 3 sig figs. Again, we see the decimal point that makes the zeros significant. And the 1.0, that's the coefficient in this number in scientific notation. And we said all digits count in the coefficient of a scientific notation number. So that's 2 significant figures, and that's the smallest number. So the final answer will have to have 2 sig figs. The calculator answer is 500. So let's count 2 sig figs. We keep the 5 and we keep 1 0 after. What comes after is the 0, so we'll keep the 0. However, you can see that there is no solution between not showing the decimal point. If you do not show the decimal point, that would be 1 sig fig. But if you show the decimal point, that would be 3 sig figs. So you have to use scientific notation. And so this will become 5.0 times 10 to the second. And this way you show that you have 2 significant figures. Let's look at the rules now when you have measurements that you need to add or subtract. So for addition or subtraction, the rule is different. The limiting term is the one with the least precise digit place, or in other words, the least number of decimal places, if you have decimal places. But it can be a digit place, so it can be in the ones place, the tens place, the tenth place, the hundredth place, etc. So let's look at example. We have 5.74 plus 0.823 plus 2.651. So you need to determine the number of decimal places you have for each, and where is the precision stops. First number has 2 decimal places. Second number has 3 decimal places. And the third has 3 decimal places. Another way to see that very easily is to add them up and align them according to their decimal point. So you align the ones, the tens, and then hundreds and thousands. And so you can see here when you align them, the least number of decimal places is 2. And you can draw a line by doing this vertically. You can draw a line between the number that has the shortest number of digits. And this shows you that you will need to keep 2 decimal places in this example. So 9.214 is the calculator answer. We need to keep 2 decimal places. What comes after is a 4. So we need to round down. So we'll have a final answer of 9.21. Next example. We have 1 decimal place in the first measurement, 3 decimal place in the next. Let's align them, and you see when you align them that indeed you need to go all the way to 1 decimal place. To make it to the least precise digit place. The calculator answer here is 0.835. So we decided we need to keep 1 decimal place, which means we only keep the 0.8 here. What comes after is a 3, so you round down, and that means you keep the 8 as it is, and so the final answer would be 0.8. Next example. So this time it's not necessarily decimal places. You can see that 1010 has digits only up to the tens, because the 0 here is not significant. Then the 2, it's in the ones place. And then minus 2.5, and here we have 1 decimal place. So the least precise is the tens place. So we will need to run to the tens place. Let's align them according to the decimal point, which is not shown for 2 and 1010, but you know they are where they are. So you align them according to the decimal point, even if it's implied. You calculate the answer, and 1009.5 is the calculator answer here. And you can see with the red line here that the tens place is the least precise digit place that you have in this example. So we will need to round to, you know, the tens place. And that's a 0 there in the tens place. What comes after in the ones place is a 9, which means you need to round up. So the 0 in the tens place will become a 1. And so the final answer is 1001. Sorry, 1010, because the 0 has become a 1, and so it's in the tens place. You do not show the decimal point because otherwise it would make the trailing 0 significant. So let's do a concept check on this and write the answer of the calculations below using the correct number of significant figures. Again, pause the video and do this work before you watch the answer. So we have addition and subtractions here. So we need to determine what is the least precise digit place. And so here we have 3 decimal places in our first number, 1 decimal place in the second, and 1 decimal place in the third. You align them according to the decimal point and do the addition and subtraction. And the calculator answer is 7.000. However, we can see visually here when you align them vertically that we need to round to the 1 decimal place, to the tens. So to the tens or to the 1 decimal place, there is a 0 there. What comes after is a 0, so you round down and it's going to be 7.0. Next example. So we have a number in scientific notation. It would be best to write this number in regular notation to be able to compare with the 500, and then the 1.710 to the third, same. We need to change that into regular notation. So 2.05 10 to the third is 2050. 500 minus 1700. So here let's determine the least precise digit place. In 2050, it's in the tens place. The 5 is the last precise digit. In 500, with the decimal point shown, it's in the ones place. The last 0 here is the last precise or significant digit. And then in 1700, it's the 7 that is the least precise digit, and that's in the hundreds place. So the least precise digit place is the hundreds place. So we need to run to the hundreds place. Let's do the calculation, and the answer is 850 when you align them according to the decimal point. You can see here 850. And let's do the red line that shows where is the least precise digit place. And because of the 1700, we need to go all the way to the hundreds place. So that means we will need to run to the hundreds place. And that's where is the 8. What comes after is a 5, so you need to round up. And so the 8 will become a 9. And then you need to show that it's 100, right? 900. So you need to add those zeros to show that you are in the hundreds place. And we don't show the decimal point, otherwise it would make it 3 significant figures, or it would change the precision to the ones place, while it should be in the hundreds place. Sorry, there's no dealing with the sig figs here. It's, you know, the least precise hundreds place is the least precise digit place. So sometimes you have mixed operation within a calculation, which means you can have addition and subtraction to do, and then multiplication and division to do within the same calculation. And so because the rules are different for each, you need to treat each separately and do them in the order that we call a PEMDAS. So PEMDAS says you need to use to do what's in parentheses first, then the exponent, the M is for multiplication, D is for division, A is for addition, and S is for subtraction. So let's look at the examples here to understand how to do this. 6.78 times 5.903 times, and then we have a subtraction to do here in parentheses. So the first thing that you need to do is what's in the parentheses according to the PEMDAS rules. So you need to do the subtraction first. So the 5.489 minus 5.01. Here we align them according to the decimal point. The answer of that intermediate calculation is 0.479. Here, if we use the rule for addition and subtraction, we need to select the least precise digit place, and it's to the 2 decimal places, right? The least precise is 2 decimal places. So because 5.489 has 3 decimal places, 5.01 has 2, and so the least is 2 decimal places. So the 7 in 0.479 is underlined to show or to remind you that you need to stop at 2 decimal places. Next, you need to do the multiplication, and then the rule change. The rule is changing, and you need to use significant figures when you're doing multiplication. So let's find out the number of sig figs in 6.78. There is, first of all, the 0.479 has 2 significant figures. It was 2 decimal places, but now you need to look at it as 2 significant figures. In the middle number here, there is 4 significant figures, and the first number has 3 significant figures. So the least number of significant figures is 2, so the final answer should be rounded to 2 significant figures. The calculator answer is this. So 2 sig figs means you keep the 1, you keep the 9. What comes after the 9 is a 1, so you need to round down. So the 9 will stay like it is, and so you will round this as 19. That's the final answer. So notice how we first used, you know, the least precise digit place, which are decimal places here. And then when we switched to multiplying, we used significant figures. Let's look at the next example. We have 19.667 minus, and then there is a multiplication to be done in the parentheses there. We need to do what's in the parentheses first. So we need to do the multiplication first. When you are doing a multiplication, you're looking at significant figures. So let's count the number of significant figures. In 5.4, there is 2 sig figs, and in 0.916, there is 3 sig figs. Multiplied together, the calculator answer is 4.9464. And so because we need to keep the least number of significant figures, we need to keep 2. And so we'll keep the 4 and the 9. However, you notice how we keep all digits until we are at the end. So we underline the 9 to remind ourselves we need to keep 2 sig figs. But now we are doing a subtraction, and it's not sig figs that matter anymore. It's, the least precise digit place. And in the first measurement here, there is, in the second measurement here, there is 1 decimal place, because when you keep 2 significant figures, it comes down to 1 decimal place. And then the first measurement has 3 decimal places. So we will need to keep 1 decimal places in the end. We do the subtraction, and here by aligning the decimal point vertically, you can see also when you use the line that shows where we were keeping 1 decimal place, it falls there. So the calculator answer is 14.7 and 14.7206, the calculator answer. You do not round until the end. So we said we need to keep 1 decimal place here because it's a subtraction. So 14.7, what comes after the 7 is a 2, you need to round down. So you keep the 7 as it is, and the final answer is 14.7. Let's do a concept check to make sure you practice this. Pause the video and do this before you watch the answer. Again, find the answer of the calculations with the correct number of significant figures. So the first example has a division to be done in parentheses first, and then a subtraction. So let's do the division first. When you are doing a division, you are watching for significant figures. 4.05 has 3 sig figs, 1.209 has 4 sig figs. When you multiply them together, the calculator answer is 3.72208. And so following the least number of significant figures, we need to keep 3 sig figs, which means we keep the 3.72. We stop at the 2. But we keep all digits, to do the calculation. We just underline the 2 to remind ourselves that we should stop there. Then we do the subtraction. And this time we need to pay attention to the least precise digit place. And here, 3.72 would have 2 decimal places, and 0.056 has 3 decimal places. So the least number is 2 decimal places. So the calculator answer is 3.66608. And we need to keep 2 decimal places. So that means we keep 0.66. What comes after is a 6. So you need to round up. So the second 6 will become a 7. And so you run this as 3.67. Next example. We have a multiplication, and we multiply that, or it's a number in scientific notation actually, multiplied by a subtraction that is in parentheses. So you need to do what's in the parentheses first. So we need to do the subtraction first. When you are subtracting, you need to look at the least precise digit place. And here, the first number has 1 decimal place. The second number is precise to the ones. So the least precise is to the ones. So the calculator answer is 30.3. So we keep the 4.10 10 to the third times. 30.3 is the answer to the subtraction. And because it needs to be rounded to the ones place, that means we round at the place of the 0 here. But now we are doing a multiplication, and the rule changes, and it's the number of significant figures that matter. And so 30.3 here has 2 sig figs, and 4.10 has 3 sig figs. So we need to keep 2 sig figs. The calculator answer is 124,230. So 2 significant figures means you keep the 1, the 2, and what comes after is a 4, so you will need to round down. So it's going to be 120,000. And you do not show the decimal point, otherwise you would make much more significant figures than you need. Final example here. We have two numbers in scientific notation multiplied together, then divided by 51,000. And then we have a subtraction and another multiplication in the next parenthesis. So it looks like we need to do two multiplications before we do the final subtraction. So we will calculate 3.2 10 to the fourth times 8.9 10 to the third divided by 51,000 on one hand. And then on the other hand, you will calculate 100 times 5. And so each of these calculations are multiplications. So what matters are the number of significant figures. So let's determine the number of significant figures for each of these numbers. 3.2 has 2 sig figs, 8.9 has 2 sig figs, 51,000 has 2 sig figs, 100 with the decimal point shown has 3 sig figs, and then 5 has 1 sig fig. So when you are doing the first calculation to the left here, you will need to keep 2 sig figs. But when you're doing the other multiplication to the right, here you will need to keep 1 sig fig. So these are the calculator answers for those intermediate multiplications here. So the first intermediate answer is 5,584.31. So we said we need to keep two significant figures for this part of the calculation. So we keep the 5 and the 5. So the second 5 is underlined to remind us that we need to keep two sig figs there. The other intermediate answer is 500. And here we need to keep 1 sig fig because of the 5. So we only need to keep the 5. Now we are doing a subtraction and the rule is changing. We need to look at the least precise digit place. And in the first intermediate answer here, we have 2 decimal places. Yes. We need to pay attention to the fact that we had rounded to 2 significant figures. That's why the 5 is underlined. So the least precise digit place is the hundreds. It's the hundreds because we underline the 5 here. And the other intermediate answer has the hundreds place as well underlined. So that means we need to keep the final answer rounded to the hundreds place. So when you calculate the answer, it's 5,084.31. If we need to round this to the hundreds, this means we keep the 5 and then the 0. What comes after the 0 is an 8, so you need to round up. So the 0 will become a 1, and that's going to be 5,100. You need to add those 2 zeros after the 1 because you need to show that the 5 is in the thousands place and the 1 is in the hundreds place. And so this is rounded to the hundreds place according to the intermediate answers.